Hello everyone, good morning. I hope you are all fine. During the last sessions, we started talking about the truss structures. We talked about truss analysis and the procedure that we have to have for analyzing trusses. Today, we are going to continue looking at a few more examples. And in one example, I'm going to use the method of joints for solving the truss, and in two other examples we are going to see how to use the method of sections for analyzing truss structures. Regarding the progress that we have in class, I think we are in a good shape and we are moving forward based on the syllabus that I posted on Canvas. And so far we have had some meetings, WebEx meetings, and I could answer some of your questions over there. And I believe a great number of you have emailed me so far asking your questions, which is good. Those of you who have not contacted me, I hope you don't have any question, but in case if you have any question or if there is anything that we need to discuss, don't hesitate to send me an email. I can answer your questions through email, or if necessary, we can schedule a time for having a WebEx meeting and discuss the questions or whatever problem that you might have about the course over there. So we have looked at some examples, and the method that we used in the previous examples was the method of joints. Just to summarize the procedure for this method, I have to say the first step is to find the reactions and draw the free body diagram. The second step is to look at the supports and find the reactions. The third step was to look at the configuration of the truss and see if there is any zero force member. And then the fourth step is to move joint by joint in the truss, write the two equations of equilibrium, summation of forces in horizontal and vertical direction equal to 0. And through this approach, we can simply look at all the members in the truss and analyze the truss. This is the summary of method of joints. And just to remind you about the two important things about truss structures, we have to mention the two properties of the truss members. The first one is that these members don't have any shear force or bending moment. Truss members are always carrying the load through axial behavior, so they are always either in tension or compression. That's one important thing about truss members. And the second important thing is the loads that are only applied at the joint. So whenever we are applying or considering the loads in truss structures, these loads are always applied at the location of the joints, and we don't have a load in the middle of a member. So let's take a look at this example and see how we can use the method of joints for analyzing this truss. In the previous examples, I said that we have to make an assumption or kind of guess which members are in tension and which members are in compression. Based on that, put the loads or forces at the joints and then start analyzing each of the joints in the truss. The thing is that your initial guess or assumption should not be always right. Actually, most of the times we will see that our guess is not correct. That's fine. But the thing that we have to always have in mind is that we have to make sure we include the right sign for the members in our calculations. We are not supposed to change our initial guess in terms of the forces that we have at the location of the joints, but we have to include the sign of the members that we obtain during the calculations in our future calculations about the truss. You will see how it works in this example that we have over here, and actually you saw it in the previous examples that I solved in this file. For this chapter, you are going to see some problems in the homework. I think it is going to be the third homework, which is very similar to what we solved in class or in these examples in the presentation files. There is one difference, and that is in the problems that I solved in the homework, and when I post the solution, you will see that I assumed all the members are in tension because we are making an assumption and it's just a yes. It doesn't matter how you start the solution. So in that problems in the homework solution, I assumed all the members are in tension at the beginning, and then based on that assumption, put the forces in the place of the joints, and then analyze the structure. And whenever I got a negative value, I could understand that that specific member was in compression, not tension, and use the negative value for that member in my future calculations. You will see that when I post the solution for homework 3, but I just wanted to say that that is another approach that we can use in analyzing truss structures. So over here you can see this example, which is this truss over here. It is asking about finding the force in each member of the truss, and you can see the configuration, the loading, and just we have to follow the steps that we had before for analyzing this truss. The first step is always drawing the free body diagram to understand the reactions and the situation of the truss. I have it over here. As you can see, we had a hinge support over here on the left and also a hinge support on the right side of the truss. It means that we have 2 reactions over here and also 2 reactions at point B. The next step is to check if this truss is determinate or indeterminate, and also checking whether it is stable or unstable. For that, we know we have to use this equation, and for using this equation, we have to put the values of M, R, and J. M is the number of members. Over here, you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So M is equal to 10. R is the number of reactions. I have 2 reactions over here at A and 2 reactions at B. So R is equal to 4. And J is the number of joints. We have 1, 2, 3, 4, 5, 6, and 7 joints in the truss. So I have to put 7 instead of J. Putting all of these values in this equation, you can see the final value for I is equal to 0, which means that the truss is stable and also determinate, which means that we can use the equations of equilibrium for solving the truss and finding all the forces in the members of the truss. So let's move forward and write the equations of equilibrium for the whole truss, because I want to find the reactions that we have over here. For that, we know there are 3 equations that we can write. One of them is summation of forces in X. The other one is summation of forces in Y or vertical direction. And the third equation is summation of moments around one point, which I usually consider left point, but it's your call. I mean, you can pick point B for finding the moments around. But let's see how we can use these equations. The first equation is over here, summation of forces in X, and let's see what we have. Over here we have the horizontal reaction at A, and that should be positive because it is to the right. 15 kilonewton over here, that should be positive because it is to the right, and we usually assume the right direction is the positive direction for X. And we also have the horizontal reaction at B. So AX, BX plus 15 equal to 0. Then we have the forces in vertical direction. For that, I have reaction at A or AY, reaction at B or BY, and 3 forces that we have over here, 10, 20, and 10. Those are listed over here. Reaction at A, reaction at B, and this is just summation of all of those forces over here, which is 40. Now I have to calculate the moments about one point. I'm looking at point A, and the moments about point A are the moments because of these reactions at B, and these loads that I have at point G, F, and E. If the moment is counterclockwise, it is positive, and if the moment is clockwise, it is negative. If you look, you can see the moments that I calculated. We have moments because of By, moments because of Bx, and the 3 moments because of these 3 forces over here. This 10 kilonewton at G, this 20 kilonewton at F, and the horizontal force at point E. We don't have any moment because of this vertical force, because if we continue the direction of this force, we can see it is passing through point A, which means that it is not creating any moment about point A. So this vertical load does not have any moment, or actually does not have any distance to point A, so it does not create any moment about point A. And the only moment that we have is because of this horizontal force over here, and the moment should be minus 15 multiplied by 8 because it is causing a clockwise moment. You can see this is the moment that I'm talking about. So now that we have these 3 equations, we can see that we have 1, 2, 3, 4 unknowns and only 3 equations, which means that just considering these 3 equations is not going to help me in finding the reactions. In such situations, we have to move forward and look at the joints, and it seems like by just writing the equations of equilibrium, we are not capable, or actually we cannot find the reactions because these equations are not enough for finding the reactions. So let's move forward and start the procedure for the method of joints. We know that whenever we want to use this method, we have to find the zero force members, and then after that we have to assume some forces in the members, assume either they are in tension or compression, and then put the reactions of the member on the joints and move joint by joint in the truss and write the equations of equilibrium. Over here you can see we have 3 zero force members. Over here you can see one over here which is Fg, and one over here which is Dg. How could we understand these are zero force member? That's based on the discussion that we had in the presentation. I said in situations where we have 2 members like this exactly after each other in the same direction, and a third member is being connected to them in a different direction, that third member is a zero force member if there is nothing on the other side of the joint. Over here you can see member CE is a zero force member because if it carries some force or load, there is nothing on the other side of joint C to balance the load or force of this member or EC. That's why EC should be a zero force member. The same idea is happening for this member at joint D or member DG. You can see members DF and DB are exactly after each other. And if we assume some force for member DG, there is nothing on the other side to balance this force on member DG. So that's why DG should be equal to 0. And now that DG is equal to 0, I can look at point G and remember the second situation about zero force members. Whenever we have 2 members exactly like this, meeting each other at the corner, and the loading is just in the same direction as this member cannot have any load or any force because there is nothing on the other side to balance the load of member FG. Right? That's how I could understand these members are zero force member. I discussed it in more details in the presentation file, and I hope this explanation kind of helps you to remember that. But if you have any question, let me know and we can discuss it more in our meetings. So I could find the zero force member, and the next step is to assume these members are in tension or compression. I just assume that these members over here that are shown by blue arrows are in compression, and these members with green arrows are in tension. Just an assumption. It doesn't matter whether you assume or consider this assumption or this approach that I have over here, or you assume something different. The important thing is to make sure you put the right direction for the arrows based on your assumption. For example, if you assume AC is in compression, then the arrows should be toward the joints. If you assume the member is in tension, then the arrows should be toward the member. That's the important thing. But once you make your guess or assumption, you have to move forward, write the equations of equilibrium for the joints. If you get a positive value, it means that your assumption or your guess is correct. And if you get a negative value, it means that the member is, for example, if you assume the member is in tension, the member is carrying the load through compression, and you have to just mention it in your solution. We never change our assumption in the figure. We just consider the right sign for the force in our calculation. So over here, I made my assumption, and this is the guess that I had for the members in this truss. And now I'm going to move forward and write the equations of equilibrium for each of these joints that I have in this truss over here. I'm going to begin with joint E over here, and the reason is that I have only two unknowns, member EF and member EA, and I have two equations of equilibrium. So with those two equations, I should be able to find the forces over here. And you can follow the same procedure. Whenever you want to start the method of joints, look for the joint that has only one or two unknowns, and then by starting from that joint, you can find the forces in the members. So I'm going to begin with joint E. Summation of forces in x direction is equal to 0. Positive is to the right, so I have to say 15 minus FEF is equal to 0. And by this equation, we can see member EF is 50 kilonewton, and the type is compression because the sign is positive, and it means that my assumption is right. The second equation is summation of forces in vertical direction equal to 0. I have to say minus 10 kilonewton plus FEA equal to 0. That's over here, and because of this, or based on this equation, we can see FEA is equal to 10 kilonewton. It is positive, which means that my assumption or my guess was correct, and the member is in compression. After finding the forces in joint E, we can move forward to another joint, and that joint is joint F. So based on joint E, we could find the members, or we could find the force in members EF and AE, and now I'm going to move to joint F and write the equations over here. The first equation is summation of forces in X. For that, we can say the force in member EF, which was 15 kilonewton, that should be positive because it is to the right, minus the horizontal component of the force in member FC, and plus the horizontal component of the force in member FD should be equal to 0. I considered negative for this one because the horizontal component of this force is to the left. I consider positive for FD because the horizontal component of this force is to the right, and that is positive. These are mentioned over here. As you can see, I have this equation and it has two unknowns. This equation and it has two unknowns. So I have to write the other equation in order to solve the problem and find these two unknown forces. The second equation is summation of forces in vertical direction. Over here you can see I have minus 20 kilonewton minus the vertical component of this force over here in member FC, and again minus the vertical component of the force in member FD. And I'll consider negative sign for these two forces because as you can see the vertical component of these forces are downward. So minus 20 minus FFC, the vertical component, and FFT, the vertical component, equal to 0. As you can see now I have two equations and two unknowns. This is a system of equation that we can solve by the methods that we know in based on in the basic calculus, or you can simply put this in your calculator and calculate it over there. But by considering these two equations, we can simply find the two unknown values as minus 25 for DF and minus 7.07 for CF. I'm getting a negative sign, right, for DF and CF, which means that my assumption about these members was wrong and these are not in tension. I assume these are in tension. As you can see, I put the green arrows, but based on the negative sign that I got over here, it means that these values are in compression. I'm not going to change the direction of these arrows, but in my future calculations, whenever I have FDF, I have to consider minus 25 kilonewton instead of FDF, right? And then after that, we have the forces in members CA and DB. As you can see, these members are exactly after these two members that we just solved. If you look at joint C and joint D, you can see CA is exactly after CF and DB is exactly after DF, and there is nothing else at the joint. DE and DG, we found these as the zero force members. So the member in CA, the force in the member CA is exactly the same as CF, and the force in member DB is equal to the force for member DF to have the equilibrium in joints C and D. That's why I have these terms over here. FCA is equal to FCF, and that is minus 707 and 7.07, and the member in DB is exactly equal to DF, and that is minus 25. And again, these are also negative, which means that my guess was wrong and these members are in compression. I assume the members are in tension, but the members are in compression. I'm not going to change the direction of arrows over here. I'm going to just only consider the right sign in my future calculations for these members. So we could look at joint E, we looked at joint F, and based on that we could find the forces in AE, EF, FCCA, FD, and DB. And now I'm going to look at joint G and see what is the situation over there. At joint G, I know that this FG is a zero force member. I know DG is a zero force member, so I can simply say summation of forces in vertical direction is equal to 0. And based on that, I can find the force in member BG. That's what I have over here. FBG is equal to 10 kilonewton. This value is positive, which means that the member is in compression, similar to what we assumed in our figure over here. So we could look at joint EFG, and now I can look at another joint which can be either A or B, but I'm going to look at joint A because these are the remaining joints in our calculation. If I look at joint A, I have two reactions, right? I have two reactions, and I know the forces in members AC and EA. So based on these, I can write the equations and find the two reactions at joint A. For that, I can say for the first equation, summation of forces in x direction equal to 0. that means AX plus the horizontal component of AC, and that is plus because this arrow that I have over here, the horizontal component of this arrow is to the right. That's what I have over here. As you can see, AX plus the horizontal component of this force. Now, we found the member in AC, we found the force in member AC as a negative value. That's what I have over here. And that's why I'm going to consider the negative instead of FAC. This positive was because of the direction we assumed based on this arrow. And now I'm going to include the negative value based on the value that we got or we found over here. Right? This is the procedure in using the method of joints and including the force that we found in other joints in our future calculations. So we have this equation over here. And now based on this, you can see the only unknown is reaction at A or horizontal reaction at A. And by solving this equation, we can see that reaction is equal to 5 kilonewton. It is positive, which means that the direction is the same as what we have over here. That's for the horizontal direction. For vertical direction, we can write the same or similar equation. We have to say AY minus FEA, because this arrow is downward, plus FAC, the vertical component, which should be FAC multiplied by 1 over a square root of 2. Right? That's what we have over here. Reaction at Y plus the force in member AC vertical component minus 10, which is the force in member EA. And whenever we want to use FAC in our calculations, we have to see that FAC is equal to minus 7.07, and that's what I have over here. Right? If I calculate this equation or solve this equation, I can find the value of AY as 15 kilonewton. Again, I'm getting a positive value, which means that the reaction is the same as what we have over here in terms of the direction. So we could find the two reactions at A, and now I can look at joint B, write the similar equations, and find the reactions at joint B, as you can see over here. Very similar to what we did for joint A. In the last step, I have just returned these values, the values that I found as the reactions at A and B, to the equations that we wrote at first for the total structure, these equation 1 and 2. If the values that we found are correct, these equations should be equal to 0. If they are not equal to 0, it means that we made a mistake somewhere. But if I return the values that I got for AX and BX and AY and BY into these equations, the values should be equal to 0, and that's what is happening over here. It means that my calculations are correct. As you can see, this is the method of joints. Nothing complicated. It takes a little bit of time because you have to move joint by joint and solve the whole truss. And this is why this method is considered as a time-consuming method, and that's why we have the second method, which is the method of sections, and we will see that in the future examples. But I think by these 3 examples you could see how to use this method. And of course, in the problems that we have in the third homework, you can see how we can use this approach in solving the truss member. Just have in mind, if this step about making the assumption or guess about members in the truss kind of is a little difficult for you, you can assume all the members are in tension at first, and then whenever you get a negative value in your calculations, it means that that member is in compression. I use this approach in solving the truss in the solution that I will post for the third homework, but this is another way to use this method of joints for solving the problems in truss structures. Let's move forward and look at the next example, which I have over here, and this is about using the method of sections for analyzing the truss. Alright, in this example, we are going to see or solve this truss over here, and as you can see in the question itself, it says find the forces in members CA, CJ, and IJ. So instead of asking or saying to find the forces in all the members, it is asking about specific members, CJ and IJ, which means that if you want to use the method of joints, you are going to obtain lots of results which are not necessary based on this question. It is just asking about two members, which kind of gives us a hint about using the method of sections. In the exam, or even in this question over here, you can see it is directly asking about using the method of sections. And in the homeworks and in the exam, if I want you to use any specific method, I will mention it in the question itself. For example, if I want you to use the method of sections in a problem like this, I will say that use the method of sections for solving the problem. But to just have it in mind about the general form of questions in truss analysis, whenever it is asking about some specific members, we have to use the method of sections to answer the question and also save a great amount of time because, as you know, the method of joints is going to take much more time because we have to solve all the joints and find the forces in all the members in the truss. So this is the question. It is asking about the forces in members CJ and IJ, CJ and IJ, and it is asking us to use the method of sections. Method of sections was to consider a section cut in the truss and then just write the equations of equilibrium for these two segments of the truss on the two sides of the section. That's it. That is the method of sections. And I'm going to apply this method over here. But the general steps that we have for this kind of procedure, the method of sections, is very similar to the method of joints. The difference is that whenever, or the fourth step that we have to apply for the method of joints, moving joint by joint, we have to change that in this step or in this method, and we have to just consider the equations of equilibrium for the sections that are being cut in the truss. So let's draw the free body diagram and see what is the situation about the reactions in the truss. I have a roller support at point A. I have a hinge support at point A and a roller support at joint G. So it means that we have two reactions at the place of the hinge support over here and one reaction at the place of the roller support or at joint G. That's what I have over here. As you can see, two reactions at A and one reaction at G. Just to see if the truss is stable or unstable, and to just show you how to use this equation, I have this step. It is not necessary, but I always repeat it in my examples to show you how to use this equation for different problems and check the condition of the truss. This is the equation for finding the situation about the truss, whether it is stable, unstable, and determinate or indeterminate. M was the number of members. Over here you can see we have 21 members, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So 21 members. R is the number of reactions, which is 1, 2, and 3. And J is the number of joints, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So J is equal to 12. And now putting these into the equation, you can see the final result is 0, which means that the truss is stable and determinate. After this, we have to look at the equations of equilibrium for the total structure to just find the reaction. So far, we had the similar steps that we had in the method of joints, and this does not make any difference in the method of sections. The difference is from the fourth step where we have to look at the members inside the truss. So we said these are the reactions in this truss, and now we have to use the equations of equilibrium for finding these reactions. The first equation is summation of forces in x direction or horizontal direction. That means I have AX, and if you look at the configuration of this problem, you can see there is no other horizontal force. So just AX equal to 0, and with this simple equation, we could find the horizontal reaction at A. The second equation is summation of forces in vertical direction. And for that, we can see there is one reaction at A, one reaction at G, and I have to also consider the summation of these vertical loads that are applied at these joints. If I do that, you can see the reaction at A, the reaction at G, and 520 kips, which are these 5 forces over here. So I have two unknowns in this equation, which means that just using this equation alone is not going to help me. So I'm going to look at the third equation, which is summation of moments about a point. I'm going to look at this joint over here, joint A. Summation of moments about this point should be equal to 0. And the forces that I have to calculate the moment for them are the reaction at G. That should be Gy multiplied by 120. That is the moment from this reaction about point A. And that should be positive because the moment that it is creating is counterclockwise, and I always assume counterclockwise as the positive direction for moment. So as you can see, this is mentioned over here, and each of these terms are basically the moment because of these forces about point A. If you do that, you can see the only unknown is this reaction at G. This is the equation, and as you can see, the only unknown is reaction at G, and by solving this, we can see the reaction at G is equal to 550 kips. And since it is positive, we can say our assumption or guess was right, and it is upward. Now we can return the value of this reaction at G into this equation that we had about summation of forces. About this equation, which is summation of forces in the vertical direction. And once I return this reaction over there, you can see the only unknown is AY. That is written over here. The only unknown is AY. And finding this reaction, we can see this is also 50 kips, which is upward. And by solving or using these equations, we could find the reactions at A and G. There is one important point about this truss which we could use before writing the equations of equilibrium, and that is the symmetric situation that we have about this truss. If you just look at the loading and look at the geometry of the truss, you can see everything is symmetric, and based on that we could simply say this AX should be equal to 0 and AY and GY should be the same. But that is just a quick kind of approach or method to solve the truss quickly and save some time. But even if we don't know that, we can simply write the general equations and find the forces and reactions as I have over here. The next step, which is the method of sections, is considering a section cut like this, which goes through the members that are being asked in the question. The question was asking about the forces in members IJ and CJ, and that's why I'm defining my section cut like this. So it is cutting the truss into two segments or portions through this cut. I'm going to just look at the left portion. see the left portion of the cut that is over here. And I'm going to assume all of these members are carrying the load in tension, IJ, CJ, and CD. That's why the forces that I'm applying from these members at the joints are toward the members. I just assume these members are in tension. That's why the forces that they apply to the joints are in these directions. And now I'm going to look at just this portion of the truss. And as you can see, the unknowns that we have over here are Fij, Fcj, and Fcd. So I'm going to write the equations of equilibrium for just this portion of the truss. As you can see, we can write the summation of forces in X, but since I have 3 unknowns, it is not going to help me. I can write the summation of forces in vertical direction. Again, I have 2 unknowns, and that is not also going to help us in terms of finding the values. But if we look at the third equation, which is summation of moments, and if we write it about point C, then you can see there will be only one unknown in the equation, because if I find the moments about point C, there is no moment because of Fcj and Fcd. There is one moment because of these 20 kips over here, one moment because of these 50 kips as the reaction at A, and also a moment because of the horizontal component of this Fij. As you can see, it has a horizontal component and a vertical component. The vertical component goes through point C. That does not create any moment, but the horizontal component of Fij will create some moment about point C. So we can write that in the equation. The equation that I'm talking about is mentioned over here. As you can see, these two are the moments because of these two forces about point C. And this term over here is the moment because of the horizontal component of Fij about point C. It is mentioned over here. It is negative because the moment because of the horizontal component will be clockwise. That's why it is negative. And the horizontal component itself can be found based on this term over here. Very similar to the way that we used before in finding the horizontal component. If you look at this member Ij, we can consider it as a triangle like this. Member Ij is over here, 5 feet is the height of the triangle, and 20 feet is the horizontal side of the small triangle for member Ij. And based on this, we can find the horizontal component as 20 over this side, which is a square root of 20 squared plus 5 squared. So if I return this horizontal component of Ij over here in this equation, the only unknown will be Fij. And by solving the equation, we can simply find Fij as minus 65.97 kips. It is minus, it means that my assumption about it is right and the member is in compression. I'm not going to change anything over here, just the sign tells us that the member is in compression, and in our future calculations, whenever we have Fij, we have to consider the negative value in our calculations. Now I'm going to write the summation of forces in vertical direction. For that, you can see we have one component because of Cj and one component because of Fij, and that is known. You could find the value of that force over here. So I'm going to write these over here, summation of forces in vertical direction, and that is just for this portion of the truss. And if I write that, you can see the vertical component of Cj, and Fij is mentioned as negative because we found it as negative, and the vertical component of that can be found by multiplying this force by this ratio over here. You can see in this equation the only unknown is Fcj, and by solving this equation we can find Fcj as positive 7.21. It is positive, which means that our guess was right, the member is in tension, and by just considering this portion of the truss, we could find the forces in members Cj and Ij as the question was asking. So without looking at all the joints in the truss, we could consider this cut in the truss and consider the sections, and then by looking at just the left section, we could answer the question. It was the method of sections. I have one more example about this method, and you can see how we can use this method in solving this example over here. Over here you can see the last example that we have about truss structures, and it is asking about finding the forces in members Fj, Hj, and Hk. And it is telling us to use the method of sections. So I need to find the forces in these three members, Fj, Hj, and Hk. It kind of shows me the section that I should consider in the truss, or the line that I have to draw to cut the truss. But before that, let's have the three basic steps that we had in all the structures, and those are finding the free body diagram, drawing the free body diagram, and finding the reactions. So this is the truss. I have one hinge support over here and one roller support. So these are the reactions, and I also have this equation to just show you how to put the values in the equation and see the situation around the truss. You know, M is the number of members, R is the number of reactions, and J is the number of joints. Calculating them, very similar to what we did in the last 4 examples, putting them in the equation, we can see the final value is 0, which means that the truss is stable and determinate. For finding the reactions, I can simply write the equations of equilibrium. Summation of forces in X equal to 0. That will be AX plus 50, 50, 50, and 25 equal to 0. Based on this, we can find the horizontal reaction at A. That is minus 175, which means that it is to the left. Then we have summation of forces in vertical direction equal to 0. That's AY plus BY, and there is no other vertical reaction, so these are the only two forces. The thing is that we have two unknowns, so we have to write the third equation for finding the unknown values. For that, I can say summation of moments about A equal to 0. I have the moments because of these forces, and also the moment because of the reaction at B. Those are written over here, and as you can see, by solving this equation, the only unknown is By, and we can find By as 204.75 kilonewton, and this is positive, which means that it is upward. So I can simply return this into this equation and find Ay as a negative of this value. So it means that Ay is downward, By is upward, and Ax is also to the left. So we could find the reactions, and now we have to draw the cut, or the line dividing the truss into sections. The target members are Fj, Hj, and Hk. So we can consider a horizontal line, and that is this section cut over here, right? That is the section cut that we have that is crossing the members that we want to find in the question, Fj, Hj, and Hk. If you look at the situation, we can also consider a section cut like this. Right? By considering a section cut like this, we can have the member Hk and also passing through the horizontal members, and then member Fi. Why did I consider this situation or consider a second section cut? That's why for analyzing the truss, we can see if I consider the section cut like this and consider the top portion, we have this situation of forces like this. These directions are based on assuming the members are all in tension. That's why I have these forces. And as you can see, we have 1, 2, 3, 4 unknown forces in this portion based on this line of cutting or section cut. And by just calculating the moments about point I can simply find one of these forces because all of these are going through point I, and the only force that is not going through point I is the member HK, or the force because of member HK. The distance from K to I is 6 plus 6, which is 12 meter. So 12 multiplied by FHK, and also the moments because of this 25 and 50 kip force should give us the value for member HK. So we could find the force in member HK. That was based on this section cut. And now I can consider this horizontal section cut. As you can see over here, this is based on this horizontal line. And as you can see, the forces that we don't know over here are member IF, FJ, HJ, and HK. HK is already known based on the first section cut that we considered over here. And now over here, I have to include that force in the section cut. That is this force over here, right? We found the member as a compression member, and the value is 16.67, so the force should be toward the joint, and the value is mentioned over here. So over here you can see I'm looking at the top portion of the truss, and I have to just find the forces in members FJ and HJ as the question asked me. If I consider and calculate the moments about point F, you can see the only unknown will be FHJ, because FJ and FIJ are going through point F. They don't create any moment about point F. The only thing that creates moment about point F is FHJ. That's what I have over here. Summation of moments about point F equal to 0, and I only have the moment because of FHJ. As you can see, I considered the two components of the force, horizontal and vertical. The horizontal is located as at 8 meter from point F. I to F is 8 meter. So horizontal component of this force is at 8 meter, or the distance from horizontal component of the force to the point is 8 meter. And the distance from vertical component of this force is IJ, or 6 meter. Right? Let's take a look at the truss. We are looking at this situation. 6 meter is distance from J to I, and 8 meter is the height of each level. So I'm calculating the moments because of components of this FHJ about point F. Based on the simple force analysis and force components that we know from statics, we know that the horizontal component of HJ is based on the triangle that we can consider over here, 6, the horizontal side, over this inclined side, and the vertical component is the vertical side, which is 8 over the inclined side, or the side that has the same direction as FHJ. So putting these two into the equation that we have over here, the only unknown will be FHJ. And if I solve that equation, we can find it as minus 62.5 kilonewton, which means that it is in compression because we assumed it is in tension. It is negative, which means that the member is in compression. And through this way, and this calculation, we could find the force in member HJ. So far, we could find the force in member HK. Then we could find the force in member HJ. And as you can see, if I consider the summation of forces in x direction, the unknowns will be FFJ and FHJ, which we already found it. So summation of forces in x equal to 0. I'm looking at this top portion of the truss that I have over here. 25 plus 50 minus the horizontal component of Fj, and then the horizontal component of Fhj. This is Fhj that we calculated already, and putting this into this equation, you can see Fj is found as 62.5 kilonewton. This is positive, which means that the member is in tension. Right? So by just considering these two section cuts, we could use the method of sections for analyzing the truss. As you can see, this method of sections, helps us a lot in terms of saving the time. It takes less time for analyzing the truss, but the more kind of tricky situation about this method is drawing the section, or how we should draw the section to efficiently find the forces in all the members that are being asked and analyze the truss for just find those target members. And I have to say this is based on experience. With solving lots of examples and more problems, you can have some vision about drawing these section cuts, and then by using this approach you can simply find the forces in the members that you want in a truss without the need of analyzing the whole truss. It was the method of sections. I think we could look at enough examples, and by now you are prepared for solving the homework problems. If you have any question, don't hesitate to send me your questions, and we can discuss it more through email or WebEx meetings.